All right, let's jump right in. Today, we're looking at something pretty mind-blowing from the world of robotics, based on some amazing research out of Science magazine. We're talking about a swarm of over 1,000 robots that can build things all by themselves. So this whole thing really boils down to one central puzzle, right? How in the world do you get a huge group to work together and build something complex when there's no one in charge, no leader giving out orders? It's like asking, how do you command an army with no general? Well, the answer, and this happens a lot in science, actually starts by just looking around us. We're going to dive into what you might call nature's collective genius. You know, the researchers behind this project just put it so perfectly in their paper. This quote really says it all. In nature, groups of thousands, millions, or trillions of individual elements can self-assemble into a wide variety of forms purely through local interactions. And that last bit, that is everything, purely local interaction. And look, this isn't some abstract high-level idea. You see this principle everywhere. Think about it. Cells coming together to build you or me, or ants linking their bodies to create a living raft to survive a flood. Or maybe the most beautiful example, that incredible coordinated dance of a flock of birds. So of course, engineers saw this brilliance in nature and thought, okay, can we build that? And they did. So let's meet the star of our show today, a swarm of 1,024 robots. Yeah, you heard that right, over 1,000. These are individual, autonomous robots. We're not talking about a handful of them, a dozen or so. This is a massive, engineered collective. And here they are. Just look at that. That's the entire swarm, all 1,024 of them, all in one place. It's just an incredible sight, and honestly, it represents a huge, huge leap forward in robotics. Okay, so we've seen the whole army. Now let's zoom way, way in. Let's look at a single soldier. This is one of them, a kilobot, sitting right next to a penny. And yeah, they're absolutely tiny. And what's crazy is that they're also super simple. I mean, they don't even have wheels. They just kind of slide around using these little vibration motors. They can't see, not really. They just sense stuff with infrared light bouncing off the surface. And get this. They can only talk to their immediate neighbors, and they can only tell how far away they are, not which direction. So that's the big question, isn't it? How do these really simple, kind of clumsy little guys manage to do something so complex together? Well, the magic, as it often is in the algorithm. It's all about the code. So it's time to look at the really elegant, simple rules that make this whole thing work. Let's break down the rules of assembly. Believe it or not, all that complex behavior we saw, it's built on just 3 really simple core behaviors. The researchers call them primitives. So first, you've got gradient formation, then edge following, and finally, localization. That's it. These 3 simple rules are all they need to pull this off. Okay, let's start with gradient formation. Imagine a few seed robots start a message like a game of telephone. As that message gets passed from robot to robot, a little counter goes up by 1 each time. What you get is every single robot in the swarm knowing exactly how many hops it is from the starting point. It's kind of like creating a digital contour map of the whole group. All right, now this is where things get really cool. Using that second rule, edge following, the robots on the outer edge of the main group start to move. They literally just hug the perimeter and follow it towards where the new shape is supposed to be. Meanwhile, all the robots still sitting in the clump, they act like a living scaffold, like a coordinate system, helping the moving ones find their way. The effect is this really beautiful dissolving motion, where the original blob just sheds robots to build something totally new. And this shot just shows the whole process perfectly. So on the left, that's the goal, right? The star shape that every robot was told to make. And on the right, you can see the swarm doing its thing. It starts as this dense, messy clump, and then, over a few hours, it just methodically rearranges itself into that perfect star. It's amazing. No boss, no commander, just those simple local rules we talked about. But, the real world is messy. It's one thing to have an algorithm that works perfectly in a computer simulation. It's another thing entirely when you have to deal with actual physics. You've got to plan for mistakes, for traffic jams, and you have to rely on teamwork. And here's a perfect example. This is something the designers didn't even predict, but something I think we can all relate to: traffic jams. Seriously, a single robot that's just a little bit slower than the others can cause a total pileup behind it. It's exactly like one person tapping their brakes on the highway. It's this fascinating real-world problem that you'd never see with just a few robots. It only shows up when you get to this massive scale. It's just a great reminder, isn't it? Even with these super smart algorithms, some problems are just universal.
Yep. Even tiny, vibrating robots get stuck in traffic.
So how do they fix this without a person running in to help? Well, they use this clever strategy called cooperative monitoring. See, a robot on its own might not even realize it's stuck, but its neighbors can see it. So by constantly checking in on each other, they can basically tell a buddy, hey, you're not moving. You might want to reboot. This kind of decentralized error correction is absolutely crucial. Without it, the whole system would just grind to a halt after a few robots failed. It's teamwork right down at the micro level, and it's what makes the entire swarm so tough. Okay, so let's pull back and look at the bigger picture here. What does all this actually mean? Because it's about way more than just making cool shapes. This is about engineering the future together. So here's the bottom line. What we're seeing is programmable self-assembly on a scale we've just never seen before. And the big takeaway is that incredible global complexity can come from incredibly simple local rules. But what's next? Well, this is a huge step towards an idea called programmable matter. I mean, just imagine a search and rescue team sending a swarm like this into a collapsed building, where the robots could form a temporary support beam or clear path for survivors. Or think about construction, using swarms to build things in places too dangerous for humans, like on Mars or the bottom of the ocean. It's really about creating these smart, adaptable systems that can build, repair, and even change their own shape on the fly. And all of that leaves us with one final, really fascinating question to think about. We just watched 1,000 simple little robots build a star. So what could 1,000,000 of them build? What about 1,000,000,000? What kind of tools or structures or even entire environments could we create once we truly learn how to command the swarm?